Thank you for joining our Airport GIS webinar presentation. Today we're going to look at the role that both LiDAR data and imagery play in Airport GIS. More specifically, we're going to look at how, when properly fused, LiDAR and imagery allow for operations in a 3D environment, which we believe is a better way of conducting Airport GIS. I'm Kent Watson. I'm with Textron Systems Geospatial Solutions. We're an industry-leading developer and integrator of advanced geospatial visualization, analysis, and exploitation technologies. We've been providing products and support for nearly 25 years across a broad spectrum of industries. Presenting today is Jonathan Gale. Jonathan has worked as a GIS analyst and solutions engineer at Textron Systems, and he's currently a senior geospatial solutions specialist and certified trainer. In addition, he teaches classes in LiDAR, radar, automated feature extraction, and geospatial intelligence for Northeastern University. Jonathan received the 2012 Textron Chairman's Award for Innovation. He has presented numerous papers on geospatial intelligence and automated feature extraction for diverse audiences nationwide. He lives near Missoula, Montana with his wife and 2 sons. We'll begin with a presentation on the topic of Airport GIS, its challenges and opportunities. At approximately the bottom of the hour, we'll move to a question and discussion segment before concluding remarks. So with that, let me hand things over to Jonathan.
Well, thank you, Kent, and thank you to all who have taken time out of their busy day to sit in on our webinar here. Again, we're looking at Airport GIS today and the use of LiDAR imagery and automated feature extraction to essentially create airport materials database elements in basically a faster way of doing this kind of work, if you will. So what we're going to look at today, so today's webinar, first we'll look at some of the challenges facing just basically folks in general doing this kind of work, and then we'll look at some of the benefits of using AFE and what you can get out of LiDAR and imagery by doing that. To kind of reinforce this, we'll look at a case study I did for Denver International Airport and then just get an idea of the results and look at kind of the value in this type of process, so to speak. And then, as Kent said, we'll have a question and discussion section towards the end. So to begin with, what are some of the challenges with Airport GIS? You know, first of all, we're talking about large, complex facilities, a lot of activity, a lot of moving parts, issues with access, a lot of different things. When we're talking about GIS, well, we're talking about basically delineating these features and having them for analysis, monitoring, and so forth. How do we get this type of data? You know, traditionally we've been doing it by hand and on foot, on the ground. So as remote sensing has begun to play more of a role in this, you're again looking at cost of data collection and acquisition. In addition to that, in the production segment, you're looking at labor costs for actually producing GIS-ready data from doing that. So we're talking about heads-up digitizing. One of the challenges there is, of course, it is time-consuming. I did it for many years. And it's also, what I learned from it is, you know, it's due to user error and inconsistency, and that's not meaning that the person digitizing is not doing a good job. It just means that each person digitizes differently, and it's based on human interpretation rather than interpretation directly from the data. And so that's kind of where feature extraction plays into this. Tools have always been an issue. It seems like to accomplish one task, we're using about 10 different tool sets, especially for heavy-duty production work like this. And coupled with the fact that, you know, in order to do aeronautical data, we need elevation data, we need survey work done and things like that. So what we're trying to dig into here is how remote sensing and remote sensing technology and machine learning can kind of help fill these voids and get some better production times for people. So when we're talking about Airport GIS, what are we talking about here? What you see here is AMDB elements, Airport Material Database Elements. Basically, just examples of some of the things I'm talking about here, and also examples of things that you can easily collect with automated feature extraction. Things like the apron element around the concourses, water bodies, vertical polygonal structures, aka buildings, things like that, taxiways, a lot of these polygonal features, if you will, in addition to guidance lines and things like that. All things that we can use with spatial analysis and so forth, but also looking at change over time for these types of facilities. And so when we're talking about these elements and things like that, what are people doing? Why is this important? Well, it's important, number one, for anybody from the FAA to just on-site GIS and analyst people that are, affiliated with the facility to have this information that is relevant, updated, current, but also because the FAA has created the AGIS, which is a central corridor database for people to put this information and draw from this information and share it so that it is readily available. So we've come a long way, but we're still needing to produce this information. So ideally, our airport material database elements are going to end up in the AGIS. And a lot of people who are doing this type of work are contractors. We're looking at Fed biz ops. We're going in and putting in bids for these contracts. We may have done it before, things like that. What we all have in common is we're looking for faster ways to do these things, but also sometimes we need new information from map products, imagery, something like that. Something may have changed. And so we're talking about using, or talking about the benefits of using AFE to alleviate some of these bottlenecks, if you will. When we're talking about feature extraction, we're talking about something that's automated, semi-automated. Machine learning, supervised learning refers to essentially digitizing training polygons, or if you have control data, you can basically hand that to the machine, run using a variety of different algorithms, and have it find all other instances throughout the data set. Now, there are very different types of machine learning and things like that. We're talking about Feature Analyst here, our product from Textron. It's looking at not only spectral values, but it's looking at object-oriented learning, meaning it's taking into account size, shape, area, spatial characteristics, in addition to spectral value to find features. So when we're doing this with automated feature extraction, we're also attributing our data on the fly. So we create layers like the apron element that you can see here. You're going to get area. You're going to have that immediately. So it's measured. With feature extraction too, we can look in an area of interest and just focus there. In this case, with the airport perimeter, we're only teaching the machine to look there. We can output to a variety of formats. Our requirements typically will need to be out in the CAD environment or open flight or something like that. We can look at change over time. We can compare imagery, look for different changes, and the learning is going to capture that. We have that information. We're talking about LiDAR and imagery. We're talking about 3D feature extraction. So we have X, Y, and Z. But with automation comes batch processing and distributed processing, meaning we can fire off the learning process on an entire stack of data, or we can farm that work out across the network to save even more time that way, and basically have the machines running doing work when we're not in the office or during off time. So the production cycle keeps rolling along, if you will, and so that's one of the major benefits here. In addition to that, there are advanced editing tools that come with it that make the quality control process much easier. So while we're on benefits, quickly, what do we get out of this data? Why is this good for Airport GIS and that? Well, first of all, with imagery, we've come a long way here. Imagery we have super high resolution imagery, like the samples that we'll show today, where we can see the deterioration of the tarmac, for example. We can see people on the ground, we can see lines, we can see runway lights, pretty much just about anything that we want to include in our airport materials database is in there. Okay, well that's great, but what about LiDAR? Well, LiDAR provides us with the height information, so we can fuse these two data sources together and get even more out of them. Coupled with automated feature extraction, we're not only saving time, but we're getting a higher accuracy product out of all of this. And so the solutions we're talking about today that are offered or shown here from Textron Systems, many have maybe heard of Feature Analyst and our other product, LiDAR Analyst, the third-party plugins to ArcGIS, pretty much made to make life easy for the GIS production specialists, the analysts, people that need to go in quickly and get information from their data. And that's kind of the heart of this. The beauty, too, is that both of these tools work together in conjunction with ArcGIS. So each process that you're doing is not only a model, but it's an exportable model that can be brought into the Arc toolbox. And more processes can be added either up or downstream to basically streamline your entire workflow. This can be used for training. It can be used for a lot of things, including batch processing. So, again, we're trying to take a lot of the button pushing out of this process, especially when we're using two types of data sources. Now with LiDAR Analyst, again, it's similar, third-party plugin. It's a tool set that's in ArcGIS. It is made for the ArcGIS user, essentially. With LiDAR Analyst, you're able to quickly take raw point data, whatever format that may be, and generate products, GIS-ready products, on the fly with attribution. That's the beauty of the tool. We're able to quickly go in, visualize as a DSM, build a DTM, hill shade them, extract buildings, trees, vegetation, different types of topographic products, contour lines, and so forth, all more or less with the click of a button. So we're able to really get in and dig into the LiDAR data quickly. As we build our layers, our GIS layers, we're masking each of them out. So we're almost building a wall-to-wall classification of the facility that is is topographically correct, if you will. There's no overlap of the vector layers and so forth. LiDAR Analyst attributes on the fly as well. So in addition to spatial characteristics, you've got all the height values. When it extracts trees and tree points, you're getting all the values of the trees from stem width, height, and even biomass. So all of this is happening at a rate of approximately 1,000 buildings per minute, 10,000 tree points per minute. So it's fast and efficient, if you will. All of this we can quickly output into 3D scenes, and we can cross-check our work as we go. And so we'll transition to our case study here. I've got a couple of little demo videos from this project as I was stepping through it, kind of showing the tools in action, if you will. The goal for the case study was just to kind of take on this problem and look at it. It's like, well, okay, what can we get out of LiDAR data? What can we get out of the imagery, and how long will it take to do this? And so what we set out to do is collect the features that you see in the list here, buildings, service roads, apron elements. Basically, the way I see it, some of the most obvious features, and as we go in, we extract them, we mask them out, and then we move on to the next one. So we're going to kind of look at the process that I went through to accomplish this, if you will. And so first of all, what are we talking about in terms of data sources? I'm a big fan of free data. This makes for a compelling case, especially in this study. So I used basically free LiDAR data and imagery from the USGS Earth Explorer, and then Nearmap, who is a web service imagery provider, was nice enough to provide us with a with several sample data sets for this area to build this proof of concept. So we're going to look at that too. The near map data is 0.7 of a centimeter, so extraordinary resolution and clarity. This data is collected at least twice per year, and so it adds a very compelling element to this workflow in and of itself. So what's our methodology? Well, we're going to define our area of interest. We're going to process the LiDAR data, process the imagery, do post-processing, cross-check, quality control, and publish to our database. Now, to step through it, when we define the area of interest, what are we looking at here? We're going to use the airport perimeter. In some cases, that shapefile may already be out there on the AGIS, or you can delineate it yourself. Oftentimes that's out there, but if we can focus the learning into that particular area, then that's going to reduce the amount of noise and false positives from the machine learning that we're going to do. This is where we kind of get our project squared away. We get our data spatially referenced so that we're ready to go. We have the area defined. Next, we process the LiDAR data, which, the way I put it, is easier. Everything that I create from the LiDAR data can be masked out so that when I do the learning and feature analyst, I'm not looking in the building areas for additional features. So we've already taken care of that. We can extract buildings super fast from the LiDAR data. So we're going to bring that data in. We're going to visualize it, creating an LAS data set or DEM and a hillshade, bare earth buildings. All of this can be automated. So once you've done it once, you've built a model that you can just recycle, either as a batch or the model itself, to just do these things. So this methodology can be automated, almost all the way down to the quality control point. So we've extracted our features and products from the LiDAR data. We're going to move on to the imagery. We've brought in the imagery. We're going to mask out the features that we derived from the LiDAR data. And we're going to use supervised learning to find runways, apron elements, all those additional things, vertical obstructions. Once we've essentially extracted all of our, our GIS elements, we're ready to do post-processing, and that consists of automated and manual cleanup steps. This is where we're going to start to finalize our data. Semi-automated means we could square up buildings, we can use aggregation to clean up noise, we can do smoothing to give our results more of either a hand-drawn appearance, or if we have line work, we can give it a rigid type of smoothing to make roads more linear and so forth. So once we've done that, we typically want to cross-check using, say, Google Earth or something else like that that may already have information in there, or we have data of our own from previous years or something like that. Give that a visual spot check. We move to our quality control portion of the cycle. This is where we're going to click through the results, do a random sampling. Quality control really depends on the control plan that you develop, you know, your checks and balances for certification and being able to sign off on that. And finally, we're going to publish to our database, and from there, those elements may be put into the AGIS or contained locally or something like that. They're integrated into the system and they're ready for analysis. And so with LiDAR feature extraction, first of all, we're going to go through and I say visualize, extract, and disseminate. So first we're going to generate a DEM with a hillshade so we can see the data. Now, you can build an LAS data set as well, but you want some type of visual representation of the data. So you can see the hill-shaded product here that's created really within minutes, one button. Next, you're going to generate a bare earth or a DTM. So you just put in the input data, set the output, choose a method, and hit OK. Typically, the default settings for this tool give the results that you see here. There's usually very little user interaction with the parameter settings, so to speak. So once we've generated a bare earth, will generate a hill shade to give us a level of detail. We want to spot check this, make sure it's clean, because our other results are going to be based on this. It's basically our groundwork. From the bare earth, we're going to do a building extraction. Hit the button, make sure our input data sources are there, choose the method, and save, and hit go. And so again, the quality of the bare earth is essential for the building results. The two methods offered are basically for places that have dense vegetation or for varying data sources. And so with 1 meter data, the results you see here are typical of what you would get with broken down multi-component rooftop geometry. And so from there, we probably visualize in 3D. LiDAR Analyst has a robust 3D viewer that will basically visualize and analyze up to 1 billion points. There's our point cloud. Now we can just right-click. We can add that building layer right into the point cloud, and there we go. So as we work through the data set, we can just add everything into 3D. We can cross-check this way. The 3D viewer can output to Google Earth, PDF, PowerPoint, a number of different formats, including OpenFly. So we're now working in a 2- and 3-dimensional environment, if you will. So imagery feature extraction. So this will be using Feature Analyst. And as I talked about before, we mask layers out that we already have, like buildings or areas that we don't want to classify. We digitize training examples, just a handful. And then with Feature Analyst, you go into the supervised learning dialog, and this gives you basically default settings for typical features, and then settings for output, input representation, which is just how the training samples are looking at the imagery. And here's where we can mask out features and look within an area of interest. We can hit run, and then that initiates the learning process. You can also preview and look in just one area at a time to kind of test the learning, so to speak. So we've got our buildings, we've got our apron elements. This just took less than a minute to extract those features. And so the workflow is now we start stepping through the rest of them. We can digitize some lines for the runways here, make sure that we do a good job, otherwise you have garbage in, garbage out. Same thing, highlight the layer, fire up the learning, and be looking for a wide linear feature in this case. And typically I start with the default settings just to see what I get. I want to make sure that I've masked out the other features and run that, and we'll get our initial result. We can use hierarchical learning to add to it, meaning that we can add areas that were not included, or we can clean up clutter. That's going to be part of our model, so that can be repeated. It can be batch processed. It can be automated, if you will. So this shows aggregation, simple. This is like the semi-automated step that I was talking about. That'll clean up kind of the small noise in the periphery and so forth. So that gives us an idea. Within a couple of minutes, we were able to do that amount of work already. So now we can change our 4-band data to show the near-infrared band. That's going to help us isolate classes such as roads. In this case, I've used lines as training examples. We're going to mask out the rest of the layers. The lines work really well for training examples to get these types of linear features. We're going to try and get a good representation of the road network, and then we're going to convert those polygons to lines. We're going to straighten those lines, and then we can add metrics and attribution to that so we can compute length. So we'll know how many segments we have, and we know how many miles of roads we have. Again, we did this just in a few minutes. And this is basically the process. We just keep working through these features. And so as we go, we're masking them out. We've already got several from the LiDAR data. we can check our attribute table, and you can see the values that we have for that as well. Here we're converting the road network to lines, and so we're able to get length from that. And so what does all of this mean? Well, when we look at our results, this is what I recorded from all these processes. We collected 10 elements, took a grand total of about an hour and a half, and that's including cleanup. And what does that mean for cleanup? Well, that means I went through and fixed everything. The line segments that were broken, bits of clutter. I was very thorough. I started at the top left of the image, worked my way from left to right, top to bottom, and did what I thought was an acceptable cleanup. So in my experience, it would be ready for the quality control process and moving more towards certification. We processed approximately 81 square kilometers, or about 53 square miles of data. It's LiDAR, 1 meter LiDAR data and imagery. And from all of that, we collected 1,183 features. Now, the actual machine extraction time you'll see is about 33 minutes. So that's the machine actually running. That's including aggregation and post-processing steps as well. I took very good notes. You can see our cleanup time here as well. Some elements didn't need cleanup time. Some of them were pretty straightforward. Taxiway holding positions, we basically were able to collect those right out of the gate. Buildings with the LiDAR data, pretty much I didn't do any editing on that. So we got 488 buildings in 12 minutes. Now, that's not 1,000 buildings. Well, there's not 1,000 buildings in there. And also it's 81 square kilometers. So that's a lot of data to process. It's also a lot of data to visualize in 3D. There are very few products that can actually handle that type of data, meaning merging it, processing and exploiting it, and visualizing it and getting results from it. So overall, an hour and a half process, and with good numbers and a number of different elements collected, 10 in all. So it's a good example of how you can take this data, work through it. If you were to do this by hand, it's going to take you a lot longer than an hour and a half. So it's something to explore. It's something to look into, and I think anybody interested in this type of work may want to look at our follow-up and see what you can learn. So with that,
thanks, Jonathan. That concludes the presentation portion of our webinar today. We're going to move now into a segment of question and discussion. To ask a question, just use the chat capability. You'll see the chat icon on the top right of your screen. As we wait for the first questions, let me just say that subsequent to today's webinar, you'll receive by email an email containing a link to the recording of this presentation, along with some links for additional product information for both LiDAR analysts and feature analysts. Now let's move back to Jonathan for our first question.
Thank you, Kent, and thank you again, everybody, for listening to this presentation. I appreciate it. Let's see. We've got one question that's come in. What does it take to get up and running in terms of deployment, training, etc. with this product? It really doesn't take much. The software itself can be downloaded from our website. It's a free download. It comes with a tutorial to show you how to get started. And the idea is once you work through the tutorial, it's going to give you an idea of the buttonology, the basics, and then from there, potential users usually submit an evaluation or demo license request, and we send a license out for say 7 to 14 days where you can work with your own data and basically try to see if you can accomplish what you need to accomplish with your own data. so you can test it out ahead of time. What I think is unique is that we fully support this, meaning guys like me are there to help you figure out the workflow so you're not just spinning your wheels. If it can't be done, it can't be done, and that's what we're there to help you with. I've done this for over a decade, and it's what I love to do. I love to help people. So that goes the same with training as well. So oftentimes you can submit data to us. We'll go through it for you. You give us a laundry list of what you want to do, ideas. We can help you kind of envision what it is, the possibilities with your workflow and so forth. We offer all aspects of training, from web-based to on-site. I even teach this information in a graduate course. There's just a lot of different ways we can do this. We have materials, we can make videos and so forth. So I would just say just contact us if you have questions. Let's see. Another question, does LiDAR Analyst process and classify raw LiDAR data, or can you only use the data after it's been classified? How well does it process terrestrial LiDAR? LiDAR Analyst can process and classify any type of raw LiDAR data. The tool goes way back to 2005. Basically when I started with this company, one of the first challenges we faced was the different types of format before standardization. LAS standardization in particular took hold. So input format can be anything from a shapefile to ASCII to LAS data, which is, pretty much typical of the offerings that are out there nowadays. In terms of terrestrial LiDAR, the tool itself is made for airborne. That doesn't mean it can't process terrestrial. I've done it before. The challenge you have with terrestrial LiDAR is high point density. And so when I've used it, I've had to decimate the point cloud, meaning I'd have to resample it. We'd have so many returns that the raster products would create, you'd almost see striping in it from the sensor. So it can be done. It can be a challenge to ArcGIS just because of the memory, but again, it can be done. On a large scale, it might be a little bit more difficult. Let's see, what type of vegetation, tree canopy, extract tools are available? The tree extraction tool in LiDAR Analyst is similar to the building extraction tool. You hit the button, it comes up with just a few parameters for the input data. And so what it does is it extracts tree points. The tree points are going to have your typical attributes, high, min, max, average height, things like that. But also it's going to have stem width and canopy width and things like that. At the same time, it extracts what's called a forest layer, which is a polygon layer. And the attribution for the forest layer is what you have with the tree points, in addition to basically how many trees per stand. So one polygon record will show how many trees are in that particular stand and so forth, but also it will measure biomass. So you have a volumetric calculation that's done on the fly from that as well. In terms of, what type of vegetation, it basically sees everything as vegetation. So there are steps that you could take, I'd say even with feature analysts, and different types of imagery from hyperspectral to, 4-band or 8-band imagery where you can do species classification and delineation and things like that. That's all, within the realms of possibility. Let's see. Does the software primarily utilize and streamline functions already available in Esri, or does it have unique functions that I cannot put together myself? Using available tools, how much time in general does it save? First of all, one thing we always set out to do is not recreate the wheel. So Esri technology and tools can be used when needed. Now, there is a contour generation tool in our product and one in 3D Analyst, but our contour tool, I guess, offers more parameters and more specifics, and it can work with different layers and so forth. So but also with our tools, every process that you do is part of the model. So that keeps it automated. Now you can add models from Esri as well, but there really isn't any overlap with the tools, so to speak. We try to create a tool set that enhances the experience of the Esri user, if anything. But the main point is that it's extracting GIS-ready raster and vector products from LiDAR data in this case. How much time in general does it save? I mean, it depends on your data set. I can process 5-10 square kilometers of LiDAR data with up to, I guess, 10 products within an hour. Most bearer processes that people do can take days, weeks, months, and I just know this from people that do that kind of work. So depends on the context of your mission, so to speak. Let's see, how well does LiDAR Analyst extract features from stereo-derived point clouds? It can do it. I haven't had a lot of this data come across my desk, so I haven't been able to validate yay or nay how well it does it. I don't have anything to compare it to, so to speak. But the tool is pretty nimble in terms of what you throw at it. But it depends, you know, the points need to have returns. It has to be all returns. There can't be any filtering. There can't be any noise. It has to basically comply with the same standards that you would with LAS standardized formatting to have a chance with it. Let's see, does the product deliver a specific data model conforming to FAA 18B? And specifically, no, but the idea is that you can build schemas that our other users, say like at NGA, that it's in compliance with. So you have another level of, I guess, filtering. So when you are creating results, they're going to be filtered through that schema, and it's going to conform to that schema, and the only things that are going to be, I guess, submitted or committed to your database are things that are going to be accepted through what you've outlined in that schema. So there's a lot of flexibility. We have a, what is the tool? There's a feature selector tool that was built just for that type of purpose. And again, we're talking about automation and stuff here too. So batch processing and distributed batch processing can operate with that type of user-defined schema. Does it conform to international specifications? You know, again, most likely I've used data from all over the world. I've had no problem processing it. I've done it for over a decade. The way I put it is the tool was made to conform to LAS standardized products. That's it. I mean, it doesn't mean that you can't throw other things to it, but it requires the same requirements that data that is, you know, certified as LAS format. So it has to have spatial referencing, all returns, all the characteristics that you'd find in LAS formatting. Let's see. I used Feature Analyst for many years. Great product for impervious feature extraction. Yes, it is. Thank you, Aaron. Yeah, Feature Analyst is great for large-scale land classification, things like that. You know, we have a user now who is going through entire counties of LiDAR data, which is quite a challenge, and I haven't seen too many people do that. We have another user who recently completed an entire land classification map for the entire state of Virginia. Massive project. It worked really well for them. So What makes these products stand out, in my opinion, since I used to do this work, I used to do it by hand, huge areas, states, is big data. It's meant to handle large data sets, but it's also meant to work on a small scale too. The idea is you work on a small scale and it expand up to the larger scale with the confidence that you get originally on the small scale.
Well, that's all for today. Thanks for attending. If other questions do come up, please don't hesitate to contact us. Also, please look for our follow-up email containing a link to today's recording of this presentation, also additional information about LiDAR and Feature Analyst. Thanks again, and have a good rest of your day.